Hello, everyone, and thanks for attending my presentation. My name is Nastaran Enshaei, and I'm presenting this work on behalf of our research group. This paper proposes an ensemble learning framework for multi-class segmentation of COVID-19 lesions from chest CT images. After a brief introduction and introducing radiological aspects of COVID-19, I will explain the problem statement and the objectives, and then we'll go through the methods and the data set we used for our experiments. At the end, I will represent the results and conclude the paper. The novel coronavirus disease appeared in 2019 in December in China and was characterized as a pandemic by World Health Organization in March 2020. So far, more than 185 people have been affected by this virus, and unfortunately, we have had more than 4 million deaths globally. Recently, emerging new variants of COVID-19 has made the situation more complicated even after starting the vaccination. We know that this is not the first global pandemic and may not be the last one. Over the past decades, we had other pandemics, epidemics such as Ebola, H1N1, and SARS. So we need to manage this pandemic with minimum loss and cost, learn lessons, and be well prepared for the potential future ones. The gold standard test for diagnosis of COVID-19 is RT-PCR test, which suffers from high false negative rate, delayed results, and not having access to enough testing kits in many areas. So WHO recommends the use of chest medical images as a complementary source of data for diagnosis and prognosis of COVID-19. Medical imaging demonstrates informative features of the disease and can play an essential role in managing the pandemic. Ground glass opacities, or GGO, and consolidation are the most common infection patterns in chest images of COVID-19 patients. Radiological studies indicate that pure GGO is more frequently appeared in the early stages of the disease, while the appearance of GGOs with consolidation is more common during the progressive stage. Also, the infection, the consolidation regimes over the lung volume can be used as a COVID-19 severity measures. Therefore, segmenting COVID-19 infection regimes and distinguishing the infection types can help identify the disease severity and stage. We can say that high contingency and increasing number of critically ill patients makes the severity assessment and outcome prediction of COVID-19 patients more necessary, which helps health professionals allocate limited medical resources more efficiently, make informed treatment decisions, and hopefully save more lives. Although medical images demonstrate informative features of the disease, their interpretation by radiologists is time-consuming and prone to error. So developing automatic segmentation model that can be used for the prognosis of the COVID-19 can speed up the severity assessment process. As mentioned, automated quantification of lung involvement can accelerate the COVID-19 severity assessment. Also, identifying different types of infection patterns can determine the stage and severity of the disease more accurately. Motivated by these, here we propose a deep learning-based framework for multi-class segmentation of COVID-19 lesions from chest CT scans, which identifies GGOs and consolidation under two classes of infection. Here you can see the overall pipeline of our proposed framework, which contains the pre-processing step and then training for individual segmentation networks, and at the end, ensembling the model's results using pixel-level soft majority voting for making the final decisions. The model takes a CT image as input and generates a mask indicating the infection regions. Each segmentation network contains an encoding path for extracting high-resolution features from CT images and decoding paths for localizing the extracted features and constructing the infection masks. For the encoding paths, we use four top performing CNN models, which are available in class applications with their pre-trained weights on ImageNet data sets. Three of these CNN models are modified variants of inception networks, and one of them is based on a densely connected network. The pre-trained weights on the ImageNets are used as the initial weights of the encoder, meaning that we keep the layers unfrozen and let them to be trained on our data sets. We trimmed off the fully connected layers from each pre-trained CNN models and replaced them with the decoder paths to construct our segmentation network. Indeed, adoption of state-of-the-art CNN models in encoding paths help the segmentation network learn the contextual information of CT images more accurately. For decoding paths, we use 4 decoding blocks, each consisting of a 2x2 upsampling layer, followed by a 3x3 convolution layer, and then a ReLU activation function and a batch normalization layer. ReLU activation function helps the model learn nonlinear patterns from images, and batch normalization speeds up the training process by normalizing the inputs of the layer. At the end of the decoding path, we use a softmax activation function to predict the probability of each pixel belongs to GGO consolidation or background class. Hard voting and soft voting are the most commonly used technique in ensemble learning. In hard voting, the class obtained the majority of the votes from individual models is considered as the predicted label for the sample. In soft voting, the class with the maximum predicted probability by individual models is considered as the sample's label. So soft voting by considering the predicted probabilities can take into account the individual model's uncertainty in ultimate decision making. Also for segmentation task where we need to predict a label for each pixel of the image. Here in our tasks, we have 512 by 512 pixels in our CT images. We can say that soft voting is computationally less expensive than hard voting techniques. So we use a pixel level soft voting for aggregating the results of our segmentation networks. We use categorical cross entropy as a loss function in our training process. Also to mitigate overfitting, we use early stopping method, meaning that the training process is stopped whenever the loss function on the validation set is not decreased over 10 epochs. We also use real-time data augmentation strategies, including zooming, shifting, and shearing to mitigate overfitting. The training and testing process is performed in a two-fold cross-validation approach. The data set we used is an open access data set, which is, to the best of our knowledge, the only publicly available CT data set for multi-class segmentation of COVID-19 lesions. It contains only 100 axial CT scans with the size of 512 by 512 pixels from 60 COVID-19 patients. The images are normalized using min-max normalization. Since we are using a very limited data set, we use only 40 images for training, 10 images for validation, and keep 50 images for the testing phase. The evaluation metrics we use for evaluating our model's performance are dissimilarity coefficient, sensitivity, and specificity metrics. Since you are comparing several networks based on several metrics, to measure the model overall performance, we use a weighted average of the metrics and call it MOP here, where the weights are determined based on the importance of the evaluation metrics in our tasks. Here, since dice coefficient and sensitivity are more focused on detecting infection pixels, we assign more weights to these metrics and consider less weights for specificity metrics. This paper represents our obtained results. As can be seen, each segmentation network may outperform the others in segmenting any infection class or their average. However, ensembling the model's results using pixel level soft voting can improve the performance for both GGO and consolidation infection regions and also their average. We also compare our work, our model with previous work, which uses the same data set with the same data split. And as it can be seen, our ensemble model can outperform the previous work considering all evaluation metrics. Here we provide a visual interpretation of our obtained results. The first row indicate the original CT image with its ground truth masks. Green areas indicate the GGO infection regions, and the yellow part shows the consolidation infection types. As it can be seen, ensembling the segmentation models output can yield a more accurate infection mask. This work proposed a multi-class segmentation framework for segmenting COVID-19 lesions under two classes of infection, GGOs and consolidations, to help health experts evaluate the disease severity faster and more accurately. The framework contains 4 individual segmentation networks with top performance pre-trained CNNs as encoders, and also a pixel level soft majority voting for combining the results and inferring the final outputs. The experimental results indicate that since each network may have some fails and successes in predicting class labels for a class of infection or a subgroup of pixels, aggregating the results improves the model overall performance. We should say that the data set we use, to the best of our knowledge, is the only open access data set for multi-class segmentation of COVID-19 lesions, which contains only 100 chest CT images. Also, we try to compensate for this problem by keeping more CT images for the test phase. Still, having a limited data set is considered a restriction of our work. Thanks for your attention.